And we are back with gases, the super exciting topic of gases. So when we're talking about gases, some things to remember, just our phase change. If we looked at a container and we drew gas particles within that, we need them to be as spaced pretty much as far away as they humanly can be. So lots of big open spaces, kind of like our current society. So with that, our properties of gases. We get some 4 important properties, most of which we've already discussed. Some of the big ones that are kind of new to us would be the low density, which makes sense if there's lots of open space. Within that given volume, we have a very small mass. So our density being mass to volume would suggest that we're looking at low densities. And then the other one that because they're so open, we're going to get uniform mixtures. So if we have multiple different gases in a container, I would expect them to mix uniformly across it. So for instance, if we had, say, 2 types of gases, we would not expect a system like this because those are now not uniformly mixed. They are split kind of half on one side and half on the other. That doesn't happen with gases. So don't do that with gases. One thing that is kind of new for gases is that gases will exert a force on the container that holds them. Because they're constantly moving, their kinetic energy goes up, which means when those particles impact things, you're getting a translation of force in the form of kinetic energy into an impact. That force is what we call pressure. Okay, so we're going to get a new measurement device, if you will, coming out with gases. When we talk about gases, it is important to acknowledge that what we are talking about are ideal gases. We're not talking about real gases. And the reason why is that real things behave very oddly. Ideal things behave according to strict rules. So let's just work with that. So when we're talking about ideal gases, these are kind of our rules that are associated with them. And real gases don't follow this. But some of these are kind of interesting, and some of them kind of stand out as things that might seem counterintuitive. So let's go ahead and start with the first one. They are super tiny molecules. That in and of itself isn't a big observation, but the big observation is actually the parenthetical. When we talk about a gas particle, it has no volume. So if I'm going to look at this closed container, let's say it has a volume of 2 liters. The instant I put a gas particle in there, well, that particle is now occupying that volume, which means the volume accessible for the next particle that goes in should be somewhat less than 2 liters because the red dot is now occupying it. Kind of makes sense? Except that gases, we say they don't have a volume, which means that blue dot that I now add has the exact same access to space as the red dot had to begin with. Okay, so that doesn't seem to make much physical sense to us, but what we're thinking about is on a much larger scale. When someone walks into our classroom, the volume of the classroom has decreased because the next person can't exist where that person is located. With the gas, because they are constantly moving and they're such a small density, we make the approximation that it doesn't matter how much gas you put into a container, the volume of the container stays constant. Okay, and that is or the volume accessible to the gas particles stays constant. And that's kind of an odd one, but it simplifies a lot of the calculations that we would end up running when we talk about volume in gases. Next one, pretty straightforward. We're just going to assume that our gas molecules move in straight lines and they're traveling in random directions. So they don't change directions unless they impact something to cause them to move. Really, this would be a corollary or a subsetting of the next rule that I've got on this list, and that's that they have no attraction for one another. So when we're talking about random or straight lines, they don't turn or have spin associated with them or get attracted one direction or another. They're moving in a straight place. two individual particles as they're moving through, regardless of how close they get, as long as they never touch, they don't affect the other atoms or the other gas particles' direction or speed. So there's no attraction there. Okay, that again is a requirement to simplify our calculations. The next one is molecules collide without losing energy. This becomes important because if our gas particles started colliding, eventually they would just stop moving, right? Because we're losing energy, right? So one of our assumptions that we put in is that that loss of energy is so minimal that we don't see it. Okay, so no loss of energy. And then the last one that we can reference here is that kinetic energy of gas particles is proportional to the temperature, meaning when it gets hotter, things move more. When it gets cooler, things move less. Okay? If we take all of these things into kind of consideration with our ideal gases, we get an interesting expression that can be solved for. This expression is something that was in chapter 8, that 1 mole of any gas equals 22.4 liters. Okay? This expression or this equality I have massive issues with. Okay? And really, if you memorize anything in this class, I don't want you memorizing this. That said, you're responsible for it, and it's an expectation, a stupid, stupid, stupid expectation. So we'll soapbox here for a little bit. Okay? This relates moles and liters. So why does this become problematic? What was the last video that you just watched? Oh, molarity. What did that relate? Moles and liters. Moles and liters. This is moles and liters, but it's for a gas. Okay? Moles and liters for molarity will work for any solution. Moles and liters for a gas, this equality only works if it's a gas. Okay? If we look at how I talked about it, I talked about molarity first. If we look at where the textbook references molarity, it's after it introduces this gas conversion. Okay? So they're saying gases are more important. Well, let's look to your experiences in labs. When was the last time you did an experiment that involved anything to do with a gas? Dramatic pause. You didn't. And you probably won't. Okay? At best, you get one experiment that deals with gases, and then that's it. Gases are harder to work with because they go everywhere. So it requires much stricter conditions, safety, glassware, equipment, like everything just goes through the roof. Which means that you probably won't be doing any experiments with gases. So why are we giving you this conversion factor? So that you have another thing to memorize for lecture and doing conversions. That's it. That's its sole purpose. Okay? If that's not bad enough, let's add in that there's a parenthetical here, meaning that this thing that we're telling you to memorize isn't always true. It's only true some of the time. When is it true? When we're at STP. I'm starting to get a little bit riled here. Okay, well, what is STP? Maybe that some of the time is the most of the time that we exist. So it's standard temperature and pressure. Well, standard, that makes sense. Okay, so everybody would use the same standard temperature and pressure. False. Depending on your training, origin of training, discipline, standard temperature and pressure changes. Okay? Chemists reference one standard temperature and pressure. Physicists will reference another. Engineers will reference another. Somebody in a different country will reference another. There is not a standard temperature and pressure. Okay? Similar to how we would define a standard measurement for length. Okay, so standard, bad term. But let's just say it's standard. Okay, and let's move on to the next one. Temperature. We can measure temperature, so we're saying we're agreeing to a certain temperature. Okay, let's just say that we accepted the standard. What's the temperature? Let this be a temperature that we are all typically at. Typically at where? In a lab? Outside the lab? Okay, in Africa, okay, in the Antarctic, because when we move to those different locations, the temperature is going to change. Okay, so I'm being unreasonable. Let's do it in a lab where we have air conditioning, temperature control. It would, of course, be ballpark room temperature, I'll even give you a 5-degree spread. We'll say anywhere between 20 degrees Celsius and 25 degrees Celsius. Heck, 20 to 30 degrees Celsius. Okay, that's fine. We'll accept that. Nope, that's not standard temperature. Guess what standard temperature is? 0 degrees Celsius. So we are telling you to memorize this equality at a condition that we don't do work at. Why? Because we want you to memorize another equality so that we can have you do conversions. It's stupid. Okay? Next one is pressure, standard pressure. 1 atmosphere, at least that one's somewhat decent. We get a decent number out of it, 1 atmosphere. Except pressure changes with altitude, so depending on where you are running your experiment, be it at sea level or be it on Mount Everest, your pressure changes. Because your pressure changes, this equality changes, which then means that equality isn't an equality. Okay? So it's a dumb, stupid thing to make you memorize, but as you might be able to tell, it's in a red box, which then means, what do you need to do? Effing memorize it. Okay? You are responsible for knowing that conversion factor. Okay? You can memorize it for this exam, and you can memorize it, or for exam 3, and you can memorize it for the final, and then please God forget it. Okay? Delete it from your brain, because it is a stupid thing to memorize. Okay? And with all of that yelling and screaming about how dumb it is, you've now probably actually memorized it, which is extra irritating to me. But deep breath. Let's move on. Okay? The gas force that we addressed in the last thing is what's known as pressure. Okay? So our pressure is going to come up, and that's where that standard that P of our STP comes from. So let's look at how we could use this conversion factor in some calculations. So, real quickly, how many liters are needed to hold 2.0 grams of hydrogen gas? Okay, so what am I being asked for? I want liters, and I'm being given 2.0 grams of hydrogen gas. And we don't have to write the gas there. Okay, so this becomes a bit challenging on deciding where to place things because the measurement and the substance aren't obvious. The substance for liters is technically going to be hydrogen. Okay, so we could place that in the numerator because that was our given piece of information, and we could just run with that. So we could then go through and say, well, I need a conversion. In that conversion, grams needs to disappear, so I'll place that in the denominator, and I would need liters to appear and place it in the numerator. Does this conversion exist? Okay. Soapbox. It exists just as much as the 22.4 liters equals to 1 mole exists. It does. It's stupid. Okay, so it doesn't exist. Okay, really, that's not something you're expected to memorize. So we would need to come up with a way that we could relate these. So we're going to have to change one of these units. Well, we did just address that liters can be related to moles of hydrogen gas. And in that, we said that 22.4 liters is 1 mole of hydrogen gas. Okay? So if we looked at our units, we actually haven't simplified anything, but we did at least bring in that liters. Okay? I still need to get rid of grams of hydrogen. I now also need to get rid of moles of hydrogen. Where do I find the relationship between mass and moles? Well, that's on the periodic table because hydrogen has a mass of 1. There are 2 hydrogens in H2, and we get 2.0 grams is 1 mole. There's our conversion factor. Ta-da! Nifty, neato. We can now punch it into a calculator, and we would get 22.4 liters for these 2 grams of hydrogen gas. Okay, because the 2's end up canceling out as well. Kind of makes sense? One thing I do want to address that's kind of neat about this thing, and it's not so much that it's neat about that conversion factor, it's neat because of the ideal gas system. What if this was elephants? Okay, moles of elephants liters of elephants. If I could somehow convert elephants into the gas phase, 1 mole of elephants would be equal to 22.4 liters. Which just seems absurd, but what we have to remember is that we're talking about it as a gas, and as an ideal gas, those elephants have no volume. So 1 mole of those elephants will equal 22.4 liters, as long as we're making the assumption that my elephant gas is ideal. Okay, so that gas particle, the substance, can be anything, which is kind of neat, but that has nothing to do with the conversion factor. That has everything to do with the assumptions that we put on gases to behave as ideal. Okay? So we now have a basic fundamental on how to deal with those conversions. So we might as well kick it up a big notch. Ta-da! New question. As I read the old question, how many liters of hydrogen are produced from the reaction of 0.165 grams of aluminum metal with dilute hydrochloric acid? In this statement, we've got a couple things going for us. Number one, we have a chemical equation, which we would need to verify was balanced, just for the record. We're also given 1.65 grams of aluminum, which we might go through and decide that we could simplify and write out as Al. And we have what we're being asked for, liters of hydrogen, which writing it in purple was a bad idea. So what I'm being asked for is the liters of hydrogen, okay, and officially hydrogen gas. How do I know it's H2? Because it doesn't say atoms. And I need to somehow use the conversion factors found in red and purple, and from memory, to go through and solve this. Okay, so with that, I'm going to let you go ahead and take a swing at that. So go ahead and hit pause or tap your space bar, stop the video, and we'll wait for you to go through and solve. Hopefully you're coming back because you're like, oh, this long pause is awkward, Mike. Why aren't you continuing to solve this? Because I'm still waiting for those people that haven't clicked pause to go ahead and click pause and solve this, or at least attempt to solve this on their own. And we're just going to say that's good enough. Okay, so if we go through and look at the given information, we have a measurement of grams, we have a substance of liters. Both of those things are different than where we ended. We have a measurement of liters and a substance of hydrogen. Okay? This means I'm going to have to do both a measurement conversion and a substance conversion. Okay? For me personally, I think the substance conversion is the easiest one to do because the substance conversion comes from the balanced chemical equation. Key word in that being the B for balanced. If we take a look at our chemical equation that's been given to us, it is not balanced, so we are responsible for acknowledging that it is not balanced and attempting to go through and balance it. When we start this, we'll notice that it doesn't balance nicely, because when I go through and do it, I don't get nice numbers for the hydrogen. So what will end up happening is this. You should spend some time to figure out how to balance that to make sure that you know that. That's going back and reviewing that old school material. Hydrogen is the substance I want on top. Aluminum is the substance I want on the bottom. Why did I pick aluminum? What was the given substance? Because it's a balanced chemical equation, I'm going to use moles as my measurement because that's what comes out of the balanced chemical equation. The numbers from my balanced chemical equation, assuming I did balance that right, okay, there are 3 moles of hydrogen and there are 2 moles of aluminum. I now have a single piece of information that I can work from. This now establishes that I now have a bit of information that I can work with. I don't want moles of aluminum. So I can look to my question and see if I'm given moles of aluminum, and I'm not. So I'm going to have to convert the moles of aluminum to something else. So that's where looking at the question can come in handy. I do have aluminum showing up, but I have it as a different measurement, grams. So how about we go to grams of aluminum? Before you start throwing the 0.165 grams of aluminum into that, realize that that thing in the red box is a single piece of information. It does not relate to the moles of aluminum. Where do I find the relationship between moles and mass? That would be on the periodic table, and if I remember correctly, I think, it's 26.98. I've been pausing it to go look it up, but I just don't feel like doing that right now. So we'll say 26.98 grams of aluminum is 1 mole, and that came from our periodic table. This is cool because that got rid of our moles of aluminum. I don't want the grams of aluminum, so that means I'm going to have to go through and add in that step as well. Grams of aluminum, so that my unit can cancel. Am I given just grams of aluminum? Of course I am, and of course I am in a different color than I'd written out, but there's our grams of aluminum canceling, 0.1165 grams. Fantastic numerator. This was a given piece of information. So do I now have the answer? Well, let's go back through and look at the work. Grams of aluminum canceled, moles of aluminum canceled, moles of hydrogen. Moles of hydrogen are not the liters of hydrogen, which means I need to get rid of the moles of hydrogen. Ideally, what do I bring in? Well, the liters of hydrogen. Where do I find the conversion factor between the liters of hydrogen and the moles of hydrogen? That would be 22.4 liters equaling 1 mole. And I now have a conversion that would now allow me to go through and do this. So if we set this up, our moles of hydrogen cancel, and liters of hydrogen would now be my answer. I could punch this into the calculator, and this time I will pause to use the magic of computers and distance learning. And in blue at the far right, I would get 0.20548 liters of hydrogen. Because I'm awesome and remember sig figs, I would go back and see that 3 sig figs was all I was allowed to keep, and my answer is actually 0.205, because 4 is less than 5 liters of hydrogen, and there is my glorious answer with all of that work. Again, the process of moving through this becomes the important aspect. Why are you putting information in for your individual solve? Guarantee that if you look this up online for how someone's going to show this work, they're going to do the red conversion on the left. After they follow the red conversion, they'll do the black. After they do the black, they'll do purple, and then they will do green. Okay? Why? Because a reflex is ultimately what it's coming down to, and that why becomes a very important question. If you want to go through and just solve these by following an algorithm, then by all means check how the internet's doing this. What I'm asking you to do is to think about why you're doing the conversions that you're doing. As long as you do all 4 of these steps in these proper numerator denominators, it doesn't matter the sequence in which you write them, as long as you know why you are placing them where you are placing them. If your reason is because you know what the answer is, then I hope you always know what the answer is. Okay? And right now, I certainly don't feel like I know the answer. So remember that. Okay, so again, think about our process behind how we solve. Standard methods give us formulas, and we try and punch in formulas. You then have to remember where all this information is stored. According to the, and it's not my method, but using dimensional analysis, it's now just a question of manipulating the information you've got, and then also knowing where to find other stuff. Okay? In the standard method, you have to memorize all of these possible formulas. In my method, all you're doing is just what is dimensional analysis, and then where to find information. Okay? There isn't a formula to memorize. It actually simplifies the amount of effort that you have to go through and do, as long as you spend the time to learn that process. Okay? And that's the point here. Learn the process. Okay? With that, we'll go ahead and move on to our pressure, because we keep talking about this pressure. Pressure is that force of our gas particles. Okay, well, interestingly enough, there is gas around us all the time. So there's always an external force. Okay, that force is what's helping to keep our individual shapes. It's what's keeping liquids as liquids. Okay, So all of those forces can be felt, even though we can't see them. Okay? And this is where we end up coming up with a way to quantify this pressure. And what we've got here is what's known as a barometer. And what barometers do is monitor that pressure or measure it. Okay? And how do we measure it? We have to make it visual. So to do that, what we're going to do is take a tube that is open at one end, and we're going to fill it with a liquid. Okay? In this case, that liquid is mercury, but let's just fill it with a liquid. We'll then invert that tube in a bath of that same liquid. Okay? And so what we would expect, because if we just inverted that tube, the liquid should fall out of said tube. But if I've now inverted it into a secondary container that has more liquid in the bottom of it, we'll notice the liquid doesn't all just fall out. And you can do this at home if you like. If you've got a glass, okay, and then a large pot, fill the pot maybe halfway with water, then fill your glass with water, and very quickly invert it carefully, don't break your glass, into the pot of water. And you'll notice that the water in the glass will actually stay above the level in the pot. And the reason for that is an external pressure. There's an external pressure from the gas pushing down on the liquid in the pot. Because it's pushing down on the liquid, this liquid, also trying to push down, now has something pushing against it. Because the liquid in the pot is now going to be pushing up on that liquid in there, preventing it from coming out. Okay? So what we could go through and do on our barometer then is just look and kind of say, well, oh, the liquid stayed up that high. It didn't fall all the way down. Okay? That in and of itself is just a neat parlor trick until we notice weather patterns. And when the weather changes, that level goes up or down depending on weather. And this is where we have meteorology as a field of science. Because what we're doing is studying how different weather patterns affect pressure and vice versa. So because we notice it changes, if we can quantify that, we could then potentially use this parlor trick and be like, tomorrow it is going to rain, and everybody laughs at you until tomorrow it rains, and then you go, oh my God, you must have known magic. Well, no, we just knew how to make observations about pressure differences and tied those pressure differences to weather patterns. So that's kind of neat, right? And that's what's happening. Because of that, though, you have to be able to quantify that difference, because maybe just a small change in pressure doesn't actually mean rain. Maybe you actually need a really large change in pressure to differentiate for rain. So that means we need to have those individual markings graduated out. Okay? How are we measuring that distance then? Well, that distance then goes to inches or centimeters, okay, or millimeters. And we'll just measure the height of our tube. We need a standard method for this. The liquid that is typically put into our barometers is mercury, and we'll look at why we pick mercury here in a second. Okay? And we just reference the height of liquid in that tube. If the height is at 29.9 inches of mercury, well, we just say we're at normal atmospheric pressure. Okay? What happens if it goes up or down? Well, that's going to help us to predict different weather patterns. Okay, so now let's move to the next aspect. Why mercury? Well, what if it wasn't mercury? Okay, that's usually the best bet. Okay, why one thing? We'll change it to something else. Let's make it water. If I had just a container of water, so now let's be less fancy, just a container of water, and we left it out on the counter, what happens to the level of water? Okay, well, it goes down because your brother came along and drank it. Keep your brother out of this, okay, or your sister, or your parent, or your dad, or you, the dog. Okay, just take that container of water, leave it on the counter, okay, and come back to it every couple days. And what you'll notice is that that water volume will drop, and eventually it will all disappear. Okay, well, why is that? What's happening is the water is transitioning into a gas. It's transitioning at a very small extent, which is why we can see it there for a while. If we'd done that with a beaker of gas, our house would probably burn down. Okay, but if we'd used gasoline, that wouldn't have lasted there very long. That we probably would have noticeably seen that level go down across the course of hours, as opposed to the water, which might be days. Okay, so there's a different property of those individual liquids. That property becomes important because when we're looking at our barometer, we need to make sure that this level of liquid at the bottom is constantly pushing up on that tube with the same force. If that level drops because the liquid is becoming a gas out here, well, now the upward force changes. If the upward force changes, the level in the tube now has some flux and change to it. It's changing not because of weather patterns, it's changing because our liquid is disappearing. Okay? And that becomes an issue. So why mercury? Well, mercury stays a liquid. It doesn't change into the gas easily. Water, on the other hand, will change the gas very, very quickly. So we now have an observation of this. We need to, of course, come up with a name for it, and this is vapor pressure. So vapor pressure is the pressure of a gas. It's pressure, so it has to be a gas, but it's coming from a liquid. So if I just have a liquid chilling, the pressure of the gas above it that came from the liquid is known as the vapor pressure. So if I have a really big vapor pressure, that means that liquid is transitioning to the gas to a large extent. Okay? As we change temperature, would we expect the vapor pressure to change? Well, 1 degree water is almost a solid. 99 degree water is almost a gas. Would I expect the amount of gas at 99 degrees to be different than the amount of gas at 1 degree? Yes. So vapor pressure has a strong temperature dependence. Okay? As we increase temperature, our vapor pressure will drastically increase as well. Okay? And so what we would just do is report the pressure of the gas coming from a liquid as our vapor pressure at an individual temperature. And so when we're talking about trying to measure weather patterns and get atmospheric pressure, we want vapor pressures of liquids to be insanely small. Okay, why do they need to be small? Well, remember, the whole point of this was that the liquid stays a liquid. Okay, it does not transition to the gas. Vapor pressure is by definition the gas. So I want a small amount of gas present, okay, for my barometry experiment or my weather pattern experiments. Okay. As a slight side note, which we will discuss later in the semester, what about dissolving gases into liquids? Okay, so this isn't really vapor pressure, okay, but we've looked at something kind of similar to this, and it's a similar concept. What happens if we dissolve solids into liquids? Okay, and in particular, what we're referencing is with temperature. What happens if I increase the temperature to the amount of solid dissolving? Okay, the solid dissolving goes up. Okay, I get more solid to dissolve at higher temperatures. What about with gases? What happens if I increase the temperature with a gas? Does the dissolving go up or down? Well, it should go up because the other one went up. It actually goes down. Okay? And this on the surface may seem contradictory, but let's think about this a little bit differently. We've got a solid transitioning to a liquid, which can transition to a gas. To go from a solid to a liquid, we are increasing temperature, right? Okay? So if I'm looking at the dissolving process, I'm taking a solid and trying to make it a liquid, I need to increase temperature. That's how we transition from solids to liquids. When I'm looking about dissolving a gas, I'm taking a gas and trying to turn it into a liquid. Well, to go from gas to liquid, I don't add heat, I remove heat. That's why the temperature needs to decrease. This is why we're seeing an apparent contradiction. It's not a contradiction if we understand how we transition between our phases with melting points and boiling points and all of that fun jazz. So that's kind of neat. Okay. That, interestingly enough, is test questions. So you should note that and remember that. Might be a good thing to add to the shared slides or shared notes. Okay. So now that we have a pressure, we need to quantify it. We already addressed some of that quantification. We can do millimeters of mercury. So measure a length of the mercury in our tube. Depending on who we talk to, because this is such a big observation and where we're making that observation, the units of pressure go absolutely bonkers. Okay, so there are tons of units for pressures, which would theoretically mean you would need to convert them all. I'm just going to blanket statement say, don't worry about it. Okay, when it comes to pressure, I really only want you to deal with atmosphere as a unit, and the reason I want you to deal with atmospheres is the number associated with that pressure unit is 1. Whereas if we look at any of the other pressure units, the standard pressure is some weird, goofy number that isn't easy to memorize. Okay? If you have to move into 151, or perhaps even into engineering, you will likely be responsible for doing these conversions. You should be able to do them, because you know dimensional analysis. Okay? But for this class, you don't have to stress about it. All I really want you to know is 1 atmosphere. Okay, so now we've got all of these things. We've got pressure, we've got temperature, we addressed volume. Okay, one thing we haven't addressed yet is the amount of particles. Okay, but we'll look at that here in just a second. Let's look at all of the things that can affect our pressure. So the pressure is the amount of times a particle impacts our wall. Okay, so this is effectively the number of impacts. Okay, so what things are going to affect that pressure? Well, how about temperature? What happens if I increase the temperature? Does that increase the number of impacts? Well, if I increase temperature, I increase kinetic energy, I increase motion. Well, the more things move, the more likely they will impact the wall. So yes, an increase in temperature is directly proportional to an increase in pressure. Okay? How about our volume? What happens if I increase the volume? How is that related to our pressure? Okay, so let's think about our container. If we had a small container, now make that container larger. Don't change anything else about the particles. Okay, so you're not adding more particles in, you're not taking particles out, you're not changing the temperature. Okay, all we're doing is changing the size of the container. What's going to happen to the pressure? Okay, and for those of you being like, well, when I blow a balloon in, it gets bigger. You're blowing particles in. That's going to be the next question. This is just volume and pressure. Okay, if I have that balloon, but now I make it bigger, okay, and stretch that out from the outside, what happens to the number of impacts on the sides of that balloon? They'll actually decrease. We've given more area, okay? And so this is best done by hand drawing visually, right? We get 4 particles in that box. If I now make that box larger, what happens to the space between those? They get much larger as well, which then means I impact the walls less frequently. So as I increase the volume, the pressure actually decreases. So this is an interesting relationship. We're getting an inverse relationship between volume and pressure. Whereas with temperature, it was a direct relationship between temperature and pressure. And I'm sure there's a better word than direct, but that's all I've got. Okay. The last one, as we started to allude to, what happens if I add more particles to that container? Notice now in this situation, I'm not changing the volume. It's the same size box. So if I increase the number of particles, and God, I wish there was a shorter way to write out the number of particles. Hold that thought. How is that going to relate to the pressure? Well, the pressure will also increase. More particles means more times the sides of that container are going to be hit, so we get a direct relationship here. Okay, between, and I'm not going to write numbers of particles again. It'd be nice if I had an analogy for this. Well, numbers of particles in chemistry we could reference as moles, which means we could write M, except M is meters. So meters was already taken. We can't use that one. Well, I could use capital M, but that was molarity. So molarity was already taken. Well, dang, what could I use? Well, let's go up to where it was originally sourced. Number of particles is what we're referencing. When we're talking about our moles or our number of particles in gases, it's N is our symbol. So a direct relationship between moles and pressure. One thing you might start to then ask, once you've got all of these relationships, is we know that there's relationships between moles and pressure and volume and pressure. So shouldn't there be a relationship between moles and volume? Yeah, there is. Shouldn't there be a relationship between temperature and volume? Yes. Good job. Isn't there also a relationship between temperature and moles? Yes. All of these things are now interrelated through that pressure concept. Okay? And so depending on the person studying these individual relationships, they made these observations and they got to attach their name to them. So we get Boyle's law and Charles' law and Gay-Lussac's law, or Guy-Lussac, however you want to do it. We get Avogadro's law. There are all sorts of laws that come out of this, which is a bit silly because all they're trying to do is establish those relationships. And really, none of them does a good job of actually tying all of those pieces together. Okay? And eventually that's what happens. Someone went through and said, well, hold up. What if I take all of those things and I put them all neatly into one giant, instead of approximate or comparison, what if I put them into a single relationship? And it turns out that we can do that. We can say PV over NT. Notice these are all of our variables: pressure, volume, moles, and temperature. And when I put them together in this fashion, they will equal a constant. And that's kind of neat. Okay? Don't worry about what that constant is yet, but let's make sure these relationships can come out. Okay? So what we're saying is that all of those things equal some number. Okay? Okay, and because I feel like it, we're gonna make it a pineapple. Okay, so we're looking at pineapples. We said pressure was directly related to moles. So if I increased the pressure, what did I have to do to moles? Well, I also had to increase the moles. Okay. Well, if this equality was true, that would have to be the case, because pineapple doesn't change. It's always pineapple. It's always constant. So if the pressure goes up by twofold, twice the pressure, the moles must go up by twice. Okay? That's kind of neat. Okay? So this relationship, believe it or not, does all of our pieces. Okay? We talked about moles and pressure. How about pressure and volume? We said those were inversely related. Well, if the moles and temperature don't have an effect on this because they're not changing, if the pressure goes up, the volume must go down, inversely related, so that this equality still equals pineapples. So all of those relationships come out of this, and that is really phenomenally cool that someone was able to put all this together to make these observations. Cooler yet is that we have experiments to show that this is actually valid, and that's fascinating. And you can do those things with different pressure sensors and syringes and all sorts of fun jazz like that, but we aren't. And we'll just say we aren't because we're stuck at home listening to this stupid lecture. So, what is that R? It's a constant value. The exact value for that R is 0.0821 with a very complex unit afterwards. Atmospheres, liters, moles, and kelvins. Why would it be so complex? Okay, well, R is this equality, right? Well, what were the units of pressure? Atmospheres. What are the units for volume of a gas? Liters. What are the units for moles? Well, moles. That was a bit of a dumb question. And the unit for temperature is going to come in as Kelvin. How do you know it was Kelvin and not, say, degrees Celsius? When we say the units were for R, that's where the units are coming from. Why do we do it as Kelvin and not degrees Celsius or degrees Fahrenheit? Well, what happens if we use degrees Celsius? Is there something colder than 0? Yes, which means the temperature value we would enter into this expression would be negative. That throws a massive monkey wrench in this equality, and it actually entirely shuts it down. Okay, so what we have to use for this is the Kelvin scale, because the Kelvin scale is not negative. Okay, we don't have negative kelvins. Okay, and that's why we end up using Kelvin. That's why we needed Kelvin, because Kelvin as a temperature scale allows this expression to become true and useful, and that's kind of neat. Okay, so what do we do with this? Well, this is now a formula. For all those people that have been dying to have a formula so that you can plug and chug, ta-da! Here it is. You can now plug and chug to your heart's delight. It might be confusing to go through and memorize it as this expression, so typically people will memorize it as PVNRT. Okay, why that particular spacing? Because that's how I was trained in high school, and in high school I was trained this because this could kind of become a pseudo name, and we get PivNert. For those of you that didn't hear that, let me try that again. PivNert. Yes, that sounds stupid. But if it helps you remember the sequence in these, all the better. Okay, this also gets rid of the fractions, so we don't have to worry about doing any kind of divisions. But it does mean in this expression, written as PivNert, that we do have to realize that if we wanted to solve for volume, we would need nRT over P. And so we would have to do some of the algebra to go through and do that solve. Okay, but that's what's cool about this, is I can rearrange that expression to solve for any one of those 4 variables as long as I have the other 3. And that's neat. Okay. The other thing that's super, super powerful here, we're actually going to see here on the next slide, because these are now just saying we're going to rearrange. So these are just rearrangements to solve for either pressure or volume, but we could rearrange it for moles or for temperature. Where this becomes incredibly useful is that I know that if I take a particular gas and I change one of those variables, the R, the constant, is still always the same, which means I can get a neato expression. Okay, and I had to advance that so we could get the bottom of that. What is that neato expression I can get? I know, since these things are both equal to R, that pressure at conditions B, volume B, NB, and TB, these two things, I could set equal to each other. Why does that become useful? I can now potentially solve for a missing or a changing variable. Okay, and that's what this question down below is saying. The volume of a container is doubled. Assume the temperature in moles are not changed. What happens to the pressure? Okay, so what we've got is a container. We'll call this conditions A, and we doubled the volume. So the container B gets bigger. Okay, what happened to the pressure? Okay, so one of the things some of you might be able to do is to reason through exactly what happened, because we talked about some of this. Because the moles are all the same, we would expect the pressure to go down because our volume went up. Okay, so that's cool. We know an approximate, I want more than that, because what your answer choices will be: the volume doubled, the volume halved, the volume quadrupled, the volume quartered. Okay, so we need a little bit more specifics behind it just decreasing. So how do we go through and do that? Okay, well, again, I'm going to give you a second here, largely because I need to go to the bathroom, to attempt to put this down. Okay, in just a few seconds, what I'll do is summarize the pieces of information found within the text. So, to simplify all of the work or the algebra behind this, I'm going to go through, instead of being referencing as PA and PB, A is the blue color, and B is the red color, and this is why I've drawn it this way. Okay, so what we can now go through and do is start to make our substitutions into the expressions shown above. Okay, so PB, okay, well, that's what I'm solving for, so I'm going to leave that one alone. Okay, VB, well, what is the volume of the red container? Well, it's twice the volume of A, so times 2VA. So these are all times in here. The moles of B, well, that would just be the moles of A. And the moles, or the temperature of B, would just be the temperature of A. Okay? So now what I can go through and do is complete out this equality. This was PV over NT. And hopefully what you notice is that our moles are the same on both sides of the equation. So I can multiply both sides by N, and those would cancel algebraically. The temperature would also do the same thing, and the pressure, or not the pressure, the volume would also do the same thing. Okay? And so what that expression now swiftly turns into is P times 2 equals P. Okay? Where red P and blue P. What was I being asked to solve for? I wanted to know the pressure at the second conditions, PB. So right now I'm not there yet. So what I would do is divide both sides by 2, and I would get that my new pressure should be 1/2 my starting pressure. Holy monkeys, I've now actually quantified how much the pressure decreased based off of using the ideal gas law. Okay, that's the point of that. That's why this is kind of neat. Okay, so with that, what we're going to do is move into the next little topic, which is super exciting for me. How many moles of neon gas occupy 2.34 liters at STP? So we just walked you through all of this fun stuff. So you should be able to go through and note that at standard temperature and pressure, we have a temperature of 273 Kelvin, because we're at 0 degrees Celsius, so it's 273, a pressure of 1 atmosphere, and we could now go through and solve into our ideal gas equation. Okay, so what I'm about to launch into is that solve, but I'm going to let it run, and during the video running, I want you, in that tiny little space above, to go through and solve this too. We are solving for the moles of neon, given that you are starting with 2.34 liters, okay, of neon. And you should be able to do some calculations out here, okay, just kind of helping you out, giving you a step, okay? And so with that, I'm going to launch into our PV equals nRT. So PV equals nRT. So this is one of those things where you might be selective and stop listening to me. That's okay. I want to solve for moles. Well, moles was that N, so I want N equals PV over RT. Okay, and now I could start to actually go through and sub stuff in here. The pressure was 1.00 atmospheres. Okay, and I'm going to do a little bit of kind of fancy footwork here, and I'm going to decide that I'm just going to do the R, which I always forget that, so hopefully I got it right here. Liters times atmospheres over moles times kelvins. And then our temperature of 273 Kelvin. And here's the little weird kind of fancy footwork I'm going to do. And then I'm going to multiply that by the volume. So I'm going to keep the volume kind of separated away from this. Okay, so let's separate that volume out. The volume should be in the numerator. What did we say it was? 2.34. And, you know, just for giggles, 2.34 liters of neon. And we'll put a 1 there. Okay. And since I've got it set up, I'm going to go through and now enter this all into the calculator. And by all of it, I'm just going to do some of it. 1 divided by 0.0821. It might be nice if I entered into the calculator, right? 82211. See, this is why I don't enter things into the calculator live streaming, because I screw it up so badly. Okay, and I, in theory, get, assuming I did this right, let's look at that. It's 0.00446,109. That's probably a bit excessive, but always got to prove a point, right? 4. If we look at the units there, the atmospheres cancel, the kelvins cancel, our liters will cancel. So at the end of this, my units are going to look a little bit weird. It's going to be 1 over moles. Okay, and then times our 2.34, because I got rid of that unit, so that unit's not there, times 2.34. And let's see, did I actually do my calculation right? That would be embarrassing, wouldn't it? Well, we'll find out here in a second, won't we? I come up with the number 0.104. I mean, we can keep running numbers out there for a little bit. And then moles. How did the moles go up? Okay. This becomes some kind of math footwork. 1 divided by 1 over 2 is actually equal to 2. I'm doing the same thing here. We're just flipping the moles out on top of this. And I'm a little bit nervous that I goofed that calculation, so I'm going to keep talking, hopefully giving you enough time that you could go through and solve this. Of course, we're going to... Okay, cool. It looks like I'm good, and I think I got the answer. Hopefully, you also already got the answer, and hopefully, you got it a hell of a lot faster than I did. Because hopefully you did none of the work that I showed. Okay? Because you were intelligent, and you went... But this was at STP. And if I remember correctly, if I am at STP, liters and moles is a conversion factor that exists, and it's 22.4 liters. It's 1 mole. And now if I go through and do my calculation, the liters cancel and I would get moles. And the number that my calculator spits out when I decide to do it in that fashion comes out to be 0.1045, but pretty dang close to the same. So who's right? Because really, I'm hoping that what you guys did was this up there, okay? And I'm going to say you cheated, and that the way I did it was the real way to do it, okay? What's going on? Who's right? Because we both ended at the same answer. Does that mean we just randomly punched things into the calculator correctly and locked into it? No. Okay. That thing that you were told to memorize, 1 over 22.4, if you enter that into the calculator, 1 divided by 22.4 gets you exactly that numerical value. That conversion factor that you are told to memorize is a direct result of the ideal gas law. And all that someone has gone through and done is simplified the calculation by picking an effectively arbitrary temperature and pressure so that they can give you numbers to memorize. Okay? So both work for the sake of this class as long as we are at STP. But if you aren't at STP, then you should be launching into the painful aspects of PV equals nRT. Okay? The majority of the time, you will be at STP because that's what we've expected you to memorize. The textbook throws a bunch of questions at you. At 1 mole is 22.4 liters and expects you to go through and just memorize and use that. There is some utility to it at STP. The full, long, painful science of it is the ideal gas law. It is PV equals nRT. That's where those relationships are coming from, and that's what you should be using. I am not going to force you to use that, though. Okay? So what do I want out of this? Your responsibility, as much as it pains me to say, is 22.4 liters of a gas is equal to 1 mole of a gas at STP. So if you can memorize that, you are good to use it. After that, I would like you to recognize the utility of PV equals nRT. Okay? That is up to you how far into PV equals nRT you want to go. But I do expect you to realize that there is a relationship between volume and temperature, volume and pressure, pressure and moles, pressure and temperature, moles and volume. Okay? All of those relationships exist, and you are responsible for all of those relationships. If you choose to memorize those as each individuals, then you are good to do so. If you instead choose to memorize PV equals nRT and understand the algebra that allows you to interpret each of those individuals, all the more power to you. I will not ask you to solve PV equals nRT. Okay? I will ask you to solve aspects of it through simple kind of relationship stuff. Okay? Which I know is a challenging line to walk. And if you are not in my lecture, for whatever reason you're watching this, you need to make sure you understand the expectations of your individual instructor. Okay? I personally, for this class, don't see the need to go all the way into solving PV equals nRT. Okay? Hopefully we'll let that sink in, and we'll move on to our next, I think, 2 slides. Dalton's law of partial pressures. Okay, a lot of this kind of stems from ideal gas. Really, all Dalton's law says is that if you want to find out the total gas pressure in an individual container, figure out the pressures of each of the individual gases. When you add all of them up, that's the total pressure. Okay? Remember, in ideal gas, no particle has a different volume, which means all particles are occupying the exact space, same space, which means they're effectively distributing the same pressure. So if I just know the pressure of, know how many atoms, regardless of what they belong to, okay, the total pressure is the sum of all of those components. Okay? But if I'm now making a balloon, say, and I want 50 parts hydrogen and 20 parts oxygen and 30 parts nitrogen, okay, the total pressure is then going to be the pressure of all of those. Okay? So if we take a look at a sample of noble gases, we'll address why noble gases here in a second, and we look at those individual pressures. If I want to know the total pressure of the entire sample, I just add all those numbers up. That's it. Like that's all you have to do. What if I know the total pressure, but I don't know one of the other substances? Well, now I do the algebra to solve for that missing substance. Okay? I'm not going to do any math solves there. You can talk to me or look for examples in the textbook to push on that. I will ask this question about the noble gas. Why would I have picked noble gases for this question as opposed to any other gas? Okay, well, the noble gases don't react with each other, so the noble gases of all our gases are the most ideal because they don't react, period. And because they don't react, that makes them a little bit more ideal. Whereas oxygen is a very reactive gas, and so if I was to look at an experiment with oxygen, it's probably going to deviate from the ideal gas law because oxygen is so reactive, that there are attractions between it and other things. Okay? So for the sake of this question, noble gases was picked to really emphasize that ideal gas relationship. We kind of addressed this a little bit, kind of not. For our Kelvin scale, we needed it to help us explain PV equals nRT. And with that, we now have an absolute scale, which is pretty awesome, that we know ends at a 0 point. And yeah, we now have an absolute 0. We don't go to negative temperatures, and that's kind of neat. Okay? So at absolute 0, we have no energy and all stuff should stop. Right? What stuff? All stuff. No motion, no energy, period, bar none, done. Okay? That sounds pretty crazy to think about because electrons are constantly moving all over the place. How could we ever have a system where we had an absolute zero where there was no motion? Exactly, that's what makes it interesting. Okay, so that's all absolute zero is. It's our theoretical limit. Okay, why theoretical? Because if everything stopped, how would we measure that it had stopped? I think we run into a Heisenberg issue there, though I've been told that's not true. I'm not quite sure I believe it, but I've been told that by people much smarter than I am, which really isn't all that hard. So we get an absolute zero. Kelvin equals 0 is as low as we get. And with that, we have now covered the entirety of Chapter 10 in probably one of the longest videos. I do apologize for that, but we're at least done